Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest and most humbling questions in all of science. Why interstellar travel may be almost impossible. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the deep darkness between the stars together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. For a very long time, human beings have looked up at the night sky and imagined movement, sailing across it, crossing it, escaping the Earth entirely and drifting toward distant suns like glowing ships on a black ocean. There is something deeply natural about that dream. Even before rockets existed, before telescopes, before electricity, people imagined travelling among the stars. Ancient stories spoke of heavenly roads and celestial kingdoms. Later came science fiction, silver spacecraft gliding effortlessly through galaxies, civilizations spreading from star to star as easily as ships crossing seas. And in many ways that idea feels inevitable. After all, human history is full of impossible journeys eventually becoming possible ones. There was a time when crossing an ocean seemed absurdly dangerous. A time when flying through the sky belonged only to birds and myths. A time when walking on the moon sounded like fantasy. And yet, step by step, invention by invention, humanity kept moving outward. So it feels reasonable to assume the stars are simply the next frontier. Farther away, yes, but still reachable, given enough time, enough intelligence, enough determination. But tonight, we're going to explore a quieter possibility, a more unsettling one. What if the problem is not engineering? What if the universe itself is resisting the journey? Because when physicists look carefully at the laws of reality, they discover something strange. The obstacles to interstellar travel are not merely practical inconveniences waiting for better technology. They may be woven directly into the structure of space-time itself. The universe appears to contain hard limits. Limits on speed, limits on energy, limits on communication. Limits that even a civilization millions of years more advanced than ours may still be unable to escape. And that realization changes the famous question completely. If intelligent life exists somewhere else in the universe, why have they never reached Earth? Perhaps the answer is not that aliens are hiding. Perhaps they are not avoiding us. Perhaps they are simply trapped, the same way we are. Because the universe is unimaginably large. Even light, the fastest thing that exists, struggles to cross it. The nearest star beyond our sun is more than 4 years away if you travel at the speed of light itself. Something no object with mass can actually do. Our own galaxy is about 100,000 light years wide. Other galaxies drift millions of light years apart in the darkness. And between them lies not empty serenity, but radiation, dust, isolation, and timescales so immense they begin to feel less like journeys and more like geological eras. You might picture the galaxy as a crowded city full of nearby neighbours, but it is closer to a vast archipelago of lonely islands separated by black oceans deeper than intuition can comfortably hold. Even sending a simple message to another nearby star would require years of waiting. A conversation between civilizations might take centuries, An explorer leaving Earth at near light speed could arrive to discover everyone they ever knew vanished long ago, not because of danger or war, but because time itself kept moving forward without them. And perhaps the strangest part of all this is that the universe does not appear hostile in an emotional sense. It is not angry. It is not cruel. It simply follows its rules with quiet consistency. The speed of light remains fixed. Energy requirements rise enormously as objects move faster. Tiny grains of dust become explosive impacts at relativistic speeds. Radiation slowly damages living tissue and machines alike. Again and again, reality seems to whisper the same message. Not forbidden, just unimaginably difficult. And yet, even within those limits, there is still beauty. Because if civilizations truly are separated by these immense distances, then every signal becomes meaningful. Every faint radio pulse drifting through space becomes an act of hope. Somewhere, perhaps around another quiet star, another civilization may also be listening to the darkness, wondering whether they are alone, staring upward with the same curiosity we feel tonight. Perhaps no one crosses the galaxy because no one can, but perhaps voices can still cross where bodies cannot. Perhaps information, stories, mathematics, music can travel farther than empires ever will. And maybe that is enough. Maybe the universe was never designed for conquest. Maybe it was designed for wonder. So tonight, we'll drift slowly through the physics of distance, relativity, energy, radiation, and time itself. Not as a lecture, but as a kind of quiet exploration into the architecture of reality. A journey into the possibility that the stars remain distant not because life is rare, but because the cosmos is vast beyond anything evolution prepared the human mind to truly feel. And as your thoughts begin to soften into the rhythm of the night, we can gently begin with the first and perhaps most important obstacle of all, the sheer scale of the universe itself. If you wanted to understand why interstellar travel is so difficult, the first thing you would need to do is forget almost every instinct your brain has about distance. Human beings evolved on a small world, a surprisingly small one. You can drive across entire countries in days, fly across oceans in hours. Messages circle the planet almost instantly. Even the moon, which once seemed impossibly distant, now feels emotionally close because we have watched astronauts walk across its surface. Our intuition was shaped by forests, rivers, mountains, and coastlines, not galaxies, and because of that, the true scale of the universe slips through the mind like water through open fingers. Take the sun, for example. Light leaving the sun takes about 8 minutes to reach Earth. That means every sunrise you have ever seen was already 8 minutes old by the time it touched your eyes. If the sun somehow vanished, Earth would continue peacefully orbiting and glowing beneath its light for 8 full minutes before darkness arrived. 8 minutes may not sound dramatic, until you remember that light moves faster than anything else in existence. In one single second, light could circle the Earth more than 7 times, and yet even at that unimaginable speed, it still takes minutes just to cross the tiny distance between Earth and its own star. Now imagine continuing farther outward, past Mars, past Jupiter and its drifting moons, past Saturn and its pale rings suspended like dust in frozen sunlight. Eventually, you reach the edge of the solar system itself, where the sun becomes less like a blazing presence and more like an unusually bright star in an enormous black sea. And still, you have not even begun the real journey, because the nearest star beyond our sun, Proxima Centauri, is more than 4 light years away. 4 years. for light, not for rockets, not for humans, for light itself. Imagine standing on one shore of a dark ocean and flashing a lantern toward another island. Then imagine waiting more than 4 years before the light finally arrives there. That is the distance to our nearest stellar neighbour, and most stars are much farther apart than that. The Milky Way galaxy alone contains hundreds of billions of stars scattered across a structure so enormous that even light requires roughly 100,000 years to travel from one side to the other. Civilizations rise and collapse on Earth in far less time. Entire species appear and disappear in far less time. If human history were stretched into a single evening, a beam of light crossing the galaxy would still be travelling long after every empire humanity has ever built had turned to dust. And beyond the Milky Way, the scale expands again. The nearest major galaxy, Andromeda, is about 2.5 million light-years away. The light entering telescopes from Andromeda tonight began its journey before modern humans even existed. Long before cities, before language, before firelight flickered in human hands, that light spent millions of years crossing darkness simply to arrive quietly in the mirrors of telescopes built by a civilization that did not yet exist when the journey began. It is difficult to emotionally process numbers like these because the brain was never designed to. The universe is not merely big in the ordinary sense, it is staggeringly, almost absurdly large. Like trying to compare a grain of sand to an ocean, or a single heartbeat to the age of mountains. And perhaps this is why interstellar travel appears so seductive in stories. Science fiction compresses these distances into manageable experiences. Ships leap between stars in hours. Conversations happen instantly across galaxies. The cosmos becomes emotionally small enough for adventure. But reality moves more slowly. Much more slowly. The universe is patient in ways human beings are not. As the vastness of the cosmos begins to settle quietly into the imagination, another realization slowly emerges beside it. Distance alone is not the only problem. Even if you could build a perfect spacecraft, even if you had endless courage, endless resources, endless patience, there is still something standing in the way. The universe has a speed limit, and unlike the speed limits painted onto roads here on Earth, this one cannot be broken by a better engine or a stronger machine. It is woven directly into reality itself. Light travels at the fastest speed anything can move. Not approximately the fastest, not currently the fastest, the absolute fastest. Nothing with mass has ever been observed exceeding it. And according to everything modern physics understands, nothing ever will. At first this feels strange. Human history trains us to believe every limit can eventually be overcome. Horses became trains, trains became airplanes, airplanes became rockets, faster and faster, century after century. So naturally, many people imagine that someday humanity will simply invent something faster than light in the same way earlier generations invented faster transportation. But relativity is not like older technological barriers. It is not a problem waiting for smarter engineering. It is more like the edge of a map, a boundary built into the geometry of existence itself. To understand why, it helps to stop thinking of space and time as separate things. In everyday life, they feel separate. Space is where things happen. Time is when things happen. You walk through space while clocks quietly tick beside you. Simple, comfortable. But early in the 20th century, Albert Einstein revealed something deeply surprising. Space and time are woven together into a single structure called space-time. Not two separate realities, but one interconnected fabric. And inside that fabric, motion behaves in ways that human intuition never evolved to expect. Imagine you're sitting quietly in a train station while another train glides past the platform. To you, it is obvious which train is moving. But in physics, motion is strangely relative. Someone inside the moving train may feel completely still while believing the station itself is sliding backward. There is no universal stillness. Everything depends on perspective. Einstein realized that if the laws of physics are to remain consistent for everyone, something extraordinary must happen. Time itself must adjust. The faster you move through space, the more slowly you move through time. This effect is called time dilation, though the phrase sounds far colder and more technical than the experience itself truly is. A softer way to imagine it might be this. Picture two clocks. One remains peacefully on Earth, the other boards a spacecraft moving incredibly fast through the darkness. When the spacecraft eventually returns, the travelling clock will show less time has passed, not because the clock malfunctioned, not because anyone tampered with it, but because time genuinely flowed differently during the journey. This is not science fiction. It has been measured repeatedly in experiments. Extremely precise clocks flown aboard airplanes drift slightly compared to clocks on the ground. Astronauts aboard the International Space Station age just a tiny fraction slower than people on Earth. The effect is usually microscopic because human technology moves far below light speed. But as velocity increases, the effect grows dramatically. At speeds close to light, time itself begins to stretch. A traveller moving at extremely high velocity might experience only a few years while decades pass back on Earth. And here the universe begins revealing something even stranger. As an object approaches light speed, accelerating it further becomes harder and harder. Not gradually difficult, violently difficult. The energy required rises enormously. It is as though reality itself resists the attempt. Imagine pushing a heavy ship across a frozen sea. At first it slides forward reasonably well, but with every increase in speed, the ice beneath it thickens. Resistance grows. The effort becomes overwhelming. Near light speed, the resistance becomes so extreme that reaching the final limit would require infinite energy. And infinity is not a practical engineering problem, it is a wall. This is why physicists say nothing with mass can actually reach the speed of light. Not because we lack ambition, but because the structure of space-time forbids it. Only massless particles, such as light itself, move naturally at that speed, and light behaves in wonderfully strange ways because of it. From our perspective, light crossing the galaxy may travel for tens of thousands of years, but from the perspective of the photon itself, no time passes at all. A beam of starlight born beside a distant sun may wander across the Milky Way for ages beyond human comprehension. Yet for the photon, the journey is instantaneous. It leaves, it arrives, no waiting in between. This idea is so unusual that the human mind almost refuses to hold on to it. Time stopping entirely feels less like science and more like poetry, and yet every experiment continues pointing toward the same conclusion. The speed of light is not simply fast, it is fundamental. Like the edge of a river current built into the universe itself. And once you begin seeing reality this way, interstellar travel changes emotionally. The stars no longer feel merely distant. They begin to feel separated by the architecture of space-time itself. You can still imagine travelling there, of course. Near light speed journeys are not forbidden in principle, but the closer you move toward that ultimate limit, the more severe the consequences become. Energy rises enormously, time distorts, radiation intensifies, tiny particles become dangerous impacts. The universe allows movement, but not easily, not casually. And perhaps that is why the night sky feels both inviting and unreachable at the same time, like seeing warm lights glowing from distant houses across an enormous frozen lake. Visible, beautiful, but separated by far more than empty space. As physicists slowly uncovered these truths during the 20th century, many began realizing something profound. The dream of crossing the stars was not simply a question of building larger rockets. It was a confrontation with the deepest structure of reality itself. And among the strangest consequences of all is what happens to time when someone actually attempts the journey. Because near light speed, travel through space quietly begins turning into travel through the future. There is something strangely emotional about the idea that time itself can move differently for different people. Not metaphorically, not psychologically, literally. For most of human history, time felt universal. Morning arrived for everyone. Clocks ticked together. A year passed equally for kings, farmers, sailors, and children asleep beneath winter blankets. Relativity quietly shattered that certainty. It revealed that time is not perfectly rigid. It stretches, compresses, flows differently depending on speed and gravity. Usually the differences are so tiny that human beings never notice them. But near the speed of light, the effect becomes extraordinary, and suddenly interstellar travel stops feeling like ordinary exploration. It begins feeling more like slipping out of sync with the rest of humanity. Imagine for a moment that a future civilization somehow builds a spacecraft capable of traveling extremely close to light speed. Not faster than light, just close enough for relativity to become dramatic. A small crew boards the vessel. Perhaps scientists, perhaps explorers, perhaps simply people curious enough to leave everything familiar behind. Their destination is Proxima Centauri, the nearest star system beyond our own. From Earth's perspective, the journey may take several years, but aboard the spacecraft, time slows. For the travellers themselves, the trip may feel far shorter. Their clocks tick more slowly relative to Earth. Their bodies age more slowly. Their conversations, meals, and quiet moments inside the ship unfold almost normally from their own perspective. And this is where relativity becomes emotionally strange. Because while the travellers experience perhaps only a handful of years, Earth continues moving forward at its ordinary pace. Parents grow older, children become adults, cities change, governments rise and fall, languages evolve, music changes. Entire generations quietly pass beneath the drifting clouds of Earth, while the travellers continue their journey through darkness. From inside the spacecraft, it might feel almost unfairly calm. The crew may celebrate birthdays beneath soft artificial lighting. They may watch recorded sunsets from Earth. They may laugh together over meals while distant stars slowly shift outside reinforced windows. Yet back home, decades may already be disappearing into history, and if the travellers eventually return, they do not truly return to the world they left. They arrive in its future. This is one of the strangest consequences of relativity. Interstellar travel near light speed functions almost like one-way travel through time, not backward, forward. A traveller could leave Earth young and come home to a civilization transformed beyond recognition. Imagine leaving in your 20s and returning to discover everyone you knew has been dead for generations. Streets renamed, languages shifted slightly, entire technologies rendered ancient. Historical events remembered the way we remember distant wars from centuries ago. You may still physically stand on Earth, but emotionally, you've become displaced in time. There is something quietly heartbreaking about that idea. The universe may permit you to cross great distances, but only by slowly severing your connection to the era you came from. And this problem grows more severe the farther you travel. A mission to nearby stars already creates painful separation. A journey across large regions of the galaxy would magnify the effect enormously. Even if advanced propulsion reduced subjective travel time for the crew, thousands or tens of thousands of years might pass outside the ship. Civilizations would transform repeatedly during that interval. Species themselves might evolve. The travelers could become like drifting messages arriving long after the original sender disappeared. And unlike fictional stories where characters casually leap between stars and return home unchanged, relativity makes every journey deeply asymmetric. Time cannot simply be paused for everyone equally. The universe keeps moving, always, patiently, silently. This creates a philosophical question rarely explored in older dreams of space travel. What does exploration mean if every journey disconnects you from your own civilization? For ancient sailors crossing oceans, home still existed when they returned. Even after years away, their culture, language, and people remained largely recognizable. But interstellar distances operate on far larger scales. A civilization attempting widespread near-light-speed exploration might slowly scatter itself across different timelines. Colonies separated by centuries of communication delay would evolve independently. Travelers would become temporal refugees from forgotten eras, and even simple conversation becomes difficult. Imagine sending a message to another civilization 4 light years away. The message travels for 4 years before arriving. Their response requires another 4 years to return. An ordinary exchange of greetings now takes nearly a decade. Longer distances stretch communication even further. A discussion between civilizations separated by hundreds of light years might unfold more slowly than geological change once did for ancient human societies. Entire governments could collapse between questions and replies. This transforms the emotional texture of the universe. The cosmos no longer feels like a bustling city waiting to be crossed. It begins feeling more like isolated islands separated not only by distance, but by time itself. And perhaps this is why the night sky feels so silent, not empty, silent. Because even if countless civilizations exist, each may be trapped inside its own local moment of history, unable to meaningfully synchronize with others across the immense depth of space-time. There is also a deeply human loneliness hidden inside relativistic travel. The travelers themselves would know this before departure. Every goodbye becomes unusually heavy. Not because the mission is dangerous, though it certainly would be, but because everyone understands the separation may become permanent in a very strange way. You're not only leaving your home, you are leaving your century. The people standing on the launch platform may grow old and vanish while only a few years pass for you aboard the ship. The Earth you return to may remember you only as a historical figure, a name in archives, a face in documentaries, a relic from another age. And perhaps that is the true emotional cost of interstellar travel, not simply energy, not simply danger, but the realization that the universe does not allow distant journeys without changing your relationship to time itself. The farther you reach into space, the more you drift away from the present shared by everyone you love. And still, despite all of this, human beings remain fascinated by the stars. Maybe because curiosity is stronger than comfort, or maybe because somewhere deep inside us, we understand that every meaningful journey has always carried a kind of separation with it, even here on Earth. And as physicists continued exploring these strange relativistic effects, another obstacle slowly came into focus beside them. Because even if humanity accepted the emotional cost of these journeys, another problem remained waiting quietly underneath: the energy required to begin the trip at all. By now, the dream of interstellar travel has already begun to feel heavier. Not impossible exactly, but burdened by distance, burdened by time, and quietly entangled with the strange architecture of relativity itself. But even before a spacecraft leaves its star system, another obstacle waits patiently beneath all the others: energy, or more specifically, the terrifying amount of energy required to move anything across interstellar distances at meaningful speeds. At first glance, rockets seem straightforward enough. You burn fuel, the fuel pushes hot gas backward, the spacecraft moves forward, simple, almost elegant. The principle itself is not especially mysterious. In fact, every rocket ever built follows the same basic idea, whether it carried astronauts to the moon or tiny satellites into orbit. The underlying physics remain surprisingly similar, and for journeys within our own solar system, rockets work reasonably well, slowly, expensively, dangerously, but well enough. The problem begins when you try to scale those journeys outward toward the stars, because rockets suffer from a quiet and deeply frustrating problem. A rocket must carry its own fuel, and the fuel itself has mass. That may sound harmless at first, but it creates a chain reaction of consequences that rapidly becomes overwhelming. Imagine trying to carry enough water across a desert for a long journey. You begin with a heavy backpack full of water bottles, but carrying those bottles makes you heavier, which means you become thirstier, which means you need even more water to compensate. Soon, part of your water supply exists only to help carry the rest of your water supply. Now imagine repeating that logic over and over again on a massive scale. That is essentially what rockets do. A spacecraft carries fuel to move itself, but it also carries fuel to move the fuel, and fuel to move that fuel, and so on. The farther and faster you want to travel, the worse this spiral becomes. Physicists call this the rocket equation, but emotionally it feels less like an equation and more like a trap hidden inside motion itself. A spacecraft intended for interstellar travel does not become mostly passengers or scientific equipment. It becomes mostly fuel, an absurd amount of fuel. And the truly difficult part is not simply cruising through space once you're moving quickly. The hardest part is acceleration. You must first push the spacecraft to enormous speed. Then, when you arrive at your destination, you must slow down again. Otherwise, you do not truly arrive at all. You simply flash past another star system at near light speed like a stone skipping across water. So now your spacecraft must carry enough fuel not only for acceleration, but also for deceleration, which increases mass, which increases fuel needs, which increases mass again. The cycle grows rapidly, almost viciously. Imagine trying to move an entire mountain by loading pieces of it onto trucks, while also needing additional trucks to carry fuel for the trucks themselves. Eventually, the transportation system becomes larger than the original cargo. This is why interstellar travel begins collapsing under its own weight, long before a launch even occurs. Even extremely efficient propulsion systems struggle against this problem. Chemical rockets, like the ones humanity currently uses, are nowhere near powerful enough for relativistic travel. They work beautifully for lifting spacecraft away from Earth, but on cosmic scales they're astonishingly slow. A modern spacecraft using conventional propulsion would require tens of thousands of years to reach nearby stars. Longer than recorded human civilization has existed, so scientists naturally began imagining more powerful energy sources: nuclear fission, nuclear fusion, antimatter, each one more energetic than the last. Fusion, the same process powering stars, could theoretically provide vastly more energy than chemical fuel. Antimatter is even more extreme. When matter and antimatter meet, they convert directly into energy with incredible efficiency. It sounds almost magical. Tiny amounts of matter releasing unimaginable power. And yet even these extraordinary possibilities struggle under the sheer scale of interstellar distances. Because near light speed, energy demands become enormous. Not large, not difficult, enormous. The kind of numbers that stop feeling intuitive altogether. Accelerating even a relatively small spacecraft to a meaningful fraction of light speed could require energy comparable to the total yearly output of entire civilizations, and that energy must somehow be generated, stored, controlled, and safely released inside a spacecraft travelling through deep space for years or decades. Even antimatter, often imagined in science fiction as a perfect solution, introduces terrifying difficulties. Antimatter annihilates instantly upon contact with ordinary matter, which means storing it safely requires elaborate magnetic containment systems operating flawlessly for enormous spans of time. A single failure would not cause a minor accident. It would produce a catastrophic explosion. And even if storage problems were solved, antimatter itself is extraordinarily difficult to produce. Humanity has only created microscopic amounts in laboratories, not kilograms, not tons, barely enough to measure comfortably. So while the laws of physics allow antimatter in principle, scaling it into an interstellar fuel source may be far beyond practical civilization-level capability. And there is another subtle realization hiding underneath all this. The universe does not reward speed gently. The faster you attempt to travel, the more dramatically energy requirements rise. It is not a linear climb. It is more like trying to sprint uphill while the hill itself becomes steeper beneath your feet. Again and again, reality seems to resist acceleration. The cosmos permits movement, but demands extraordinary payment for it. And suddenly the romantic image of starships crossing the galaxy begins to feel different. Less like elegant exploration, more like a civilization pouring unimaginable resources into moving fragile habitats through lethal darkness at nearly impossible speeds. Not because humanity lacks intelligence, but because the universe itself appears stubbornly expensive. This realization changes the emotional tone of interstellar travel in a profound way. The stars are not unreachable in the same sense that a locked door is unreachable. They are unreachable the way distant centuries are unreachable. The barrier is not merely effort, it is scale, physics, time, energy, the deep structure of reality quietly insisting that vast distances remain vast. And even if some future civilization somehow solved the propulsion problem, another terrifying realization would still remain waiting in the darkness ahead. Because space itself is not truly empty. As the idea of propulsion begins to settle into place, another realization slowly rises beneath it. The problem is not simply that spacecraft need fuel. The deeper problem is that the universe charges an almost unimaginable price for extreme speed, especially speeds approaching that of light. And this is where interstellar travel starts feeling less like engineering, and more like trying to bargain with the fundamental structure of reality itself. In everyday life, motion feels cheap. You stand up from a chair, you walk across a room, you ride a bicycle down a quiet street. Even driving a car across an entire country feels manageable because the energy involved remains comfortably within human scales. But cosmic motion belongs to an entirely different category. The energy needed to move objects through space rises dramatically as speed increases. At low speeds, the increase feels ordinary enough. But near light speed, the universe begins behaving differently. It becomes increasingly unwilling to let massive objects move faster. Imagine pushing a small boat away from shore. At first the water parts easily. The boat glides forward with gentle resistance. But now imagine the ocean somehow becoming thicker the faster the boat moves. The water transforms from liquid into something more like invisible syrup, then wet cement, then nearly solid glass. Every increase in speed demands disproportionately more effort than the last. That is roughly what relativistic motion feels like from the perspective of physics, and eventually, near the speed of light, the required energy becomes so enormous that it approaches infinity. not metaphorically, mathematically. Which means no civilization, no matter how advanced, can simply push a little harder and break through the barrier. The wall itself grows infinitely steep. This is one reason physicists sometimes describe light speed not merely as a speed limit, but as part of the geometry of reality itself. Now, to truly appreciate how overwhelming this becomes, it helps to think in terms of scale rather than equations. Imagine a relatively small spacecraft, not a giant science fiction cruiser with cities and forests inside. Just a compact interstellar probe weighing roughly as much as a large car or small truck. To accelerate even something that modest to near light speed would require staggering amounts of energy. Not the energy of a city, not the energy of a nation. Potentially energy comparable to what entire human civilizations consume over enormous stretches of time, and that energy must somehow be concentrated into one machine, one journey, one fragile vessel crossing darkness. The numbers become so large that the human brain begins losing emotional contact with them. Scientific notation can describe the quantities precisely, but precision does not automatically create understanding. Saying a spacecraft requires vast quantities of joules does not truly communicate the feeling of the problem. So perhaps it is better imagined another way. Picture trying to move a mountain using only fireworks. No matter how many fireworks you gather, the mountain barely notices. That is the emotional relationship between ordinary human energy systems and relativistic travel. Even nuclear energy, which already feels incredibly powerful by human standards, struggles against these scales. A tiny amount of uranium can power entire cities. Nuclear fusion powers stars themselves. Yet even fusion begins looking insufficient when the goal is accelerating large spacecraft close to light speed. This is why antimatter fascinates physicists so deeply. Antimatter represents the most efficient energy process currently known in physics. When matter and antimatter meet, they vanish into pure energy. It is the closest thing the universe offers to complete conversion between mass and power. Einstein's famous insight that matter itself contains enormous hidden energy becomes fully visible in these reactions. A surprisingly small amount of matter contains astonishing amounts of energy locked quietly inside it, enough to power cities, enough to devastate landscapes, enough perhaps to push spacecraft toward relativistic speeds. But once again, reality introduces another difficulty. Antimatter is extraordinarily difficult to create. Humanity can produce only microscopic traces of it using enormous particle accelerators that themselves consume vast amounts of electricity. Creating even tiny quantities requires tremendous effort, and storing antimatter safely may be even harder. Ordinary matter touches antimatter, and both disappear violently into energy. So antimatter cannot simply sit inside ordinary fuel tanks. It must be suspended carefully using magnetic fields, isolated from every surface around it like a drop of lightning held inside an invisible cage. For days, months, years, perhaps decades, a single containment failure would instantly release catastrophic energy. And all of this still ignores another brutal reality. A spacecraft must survive the acceleration itself. Human bodies are delicate. Even moderate acceleration sustained over long periods becomes dangerous. Bones, blood flow, organs and nervous systems all evolved under Earth gravity. Push too hard, and the body begins struggling to cope. This creates another hidden limitation. Even if a civilization possessed enormous energy reserves, travelers themselves might still require relatively gentle acceleration simply to survive the trip, which stretches travel times even further. and suddenly interstellar travel begins resembling something strange and almost tragic. A civilization gathers unimaginable resources, builds an extraordinary machine, spends decades accelerating it carefully through darkness, only to send a tiny number of fragile beings toward a destination they may never emotionally reconnect with. The ratio feels almost absurd, and yet, despite these difficulties, human imagination keeps returning to the stars again and again. Perhaps because curiosity itself is difficult to extinguish, or perhaps because intelligence naturally pushes against boundaries, even when those boundaries appear impossibly large. Still, the deeper physicists examine these energy requirements, the more they begin suspecting something unsettling. Interstellar travel may not simply be hard in the temporary way climbing Mount Everest is hard. It may belong to an entirely different category of difficulty, the kind built permanently into the laws of nature, a challenge not awaiting better tools, but fundamentally constrained by the architecture of space-time, energy, and mass themselves. And even if some distant civilization somehow accepted these staggering costs, even if they solved propulsion, storage, acceleration, and survival, they would still face another problem waiting quietly ahead in the darkness. Because at near light speed, even the emptiness between stars stops being gentle. When most people imagine space, they imagine emptiness, a perfect vacuum, a vast, silent darkness with almost nothing inside it. And compared to Earth, space really is astonishingly empty. Between the stars there are no oceans, no forests, no weather systems drifting across skies. Interstellar space contains only sparse traces of matter spread across unimaginable distances. But almost empty is not the same thing as truly empty. And at relativistic speeds, even the smallest fragments of matter become terrifying. This is one of the strangest transformations in all of physics. Speed changes the meaning of objects. A grain of dust resting quietly on a windowsill feels harmless. A speck of sand carried by wind barely catches your attention. Tiny particles drift through sunlight every day without consequence. But near the speed of light, those same particles become violent. Not because they changed, because you did. Imagine driving through rain. At walking speed, raindrops feel soft, barely noticeable. But on a highway, the same droplets strike your windshield with much greater force. Increase the speed enough, and even small impacts begin feeling sharp and dangerous. Now extend that idea to cosmic extremes. A spacecraft moving close to light speed through interstellar space encounters particles with enormous relative energy. Tiny bits of dust suddenly carry the impact force of explosives. A microscopic grain no larger than smoke ash could strike with catastrophic energy. Something the size of a grain of sand could release destruction comparable to powerful weapons here on Earth. And the truly unsettling part is this: you cannot simply steer around these particles. Interstellar space is filled with them. Thinly scattered, yes. But over distances measured in light years, a spacecraft would encounter enormous numbers of microscopic impacts during its journey. At ordinary human speeds, this would not matter much. But at relativistic speeds, every collision becomes magnified by terrifying amounts of kinetic energy. The darkness itself becomes dangerous. Suddenly the dream of elegant starships gliding smoothly through empty space begins to feel unrealistic. The faster the ship moves, the more hostile the environment becomes. Space transforms into a kind of invisible minefield, not crowded enough to see, but crowded enough to kill. This creates another painful engineering problem: shielding. A spacecraft travelling near light speed would require protection against radiation, dust, and high-energy particles constantly striking its forward surface. Heavy armour might help absorb impacts, but heavy armour also increases mass, and greater mass requires more energy to accelerate, which requires more fuel, which increases mass again. The cycle quietly returns. Again and again, the universe seems to pull every solution back into the gravity of the same fundamental limitations. Some scientists have imagined elaborate protective systems, magnetic fields capable of deflecting charged particles, sacrificial shields placed far ahead of spacecraft to absorb impacts before they reach the main vessel, clouds of particles projected forward like protective mist. And while some of these ideas may help, none remove the underlying problem entirely. At near light speed, interstellar space simply stops behaving gently. Even hydrogen atoms, the most common particles in the universe, become dangerous at sufficiently high velocity. Radiation intensifies, impacts multiply. The environment grows increasingly violent the faster you attempt to move through it. The cosmos does not merely resist speed through energy requirements, it weaponizes the emptiness itself, and beyond dust, there is radiation, a quieter danger, invisible, constant, ancient. Earth feels safe largely because our planet protects us extraordinarily well. The atmosphere absorbs harmful radiation from space. Earth's magnetic field deflects many charged particles away from the surface. We live at the bottom of a deep protective ocean of air without usually noticing it. But beyond that protection, space becomes harsher. Cosmic rays continuously stream through the galaxy at enormous energies. Some originate from exploding stars, others from black holes, neutron stars, and violent cosmic events scattered across distant regions of the universe. These particles move incredibly fast, carrying enough energy to damage cells, disrupt electronics, and slowly degrade living tissue over time. Astronauts aboard the International Space Station already experience increased radiation exposure despite remaining relatively close to Earth. A deep interstellar mission lasting years or decades would expose travelers to vastly greater cumulative doses. And radiation is particularly cruel because it often works slowly, quietly, not like an explosion, more like erosion, cells damaged one by one, DNA altered gradually, electronics accumulating tiny failures over long spans of time. The danger accumulates invisibly in darkness. For machines, this creates enormous reliability challenges. Circuits fail, memory corrupts, sensors degrade, tiny errors spread slowly through complex systems. On Earth, engineers solve these problems through maintenance and replacement. Broken components can be repaired, systems upgraded, infrastructure rebuilt, but interstellar spacecraft travel alone. There are no repair stations drifting between stars, no emergency rescue teams, no spare civilization waiting nearby. A ship crossing deep space must survive almost entirely on its own, year after year, decade after decade, possibly longer, and this introduces another quiet enemy into the story. Entropy, the slow tendency of all systems toward disorder. Metal fatigues, materials crack, machines wear down. Even perfectly built systems slowly drift toward failure over sufficient spans of time. Human civilization itself survives through constant maintenance. Roads are repaired, buildings restored, power systems monitored continuously. Without upkeep, even our greatest structures decay surprisingly quickly. Now imagine maintaining a fragile technological ecosystem isolated in interstellar darkness for generations. The challenge becomes staggering. And gradually, the emotional image of interstellar travel changes once again. The universe no longer feels like an open sea waiting for explorers. It begins feeling more like a freezing mountain range crossed only at immense risk. Beautiful, silent, but fundamentally unforgiving. And perhaps this is one reason the cosmos appears so quiet. Maybe civilizations do exist. Maybe countless worlds gaze upward beneath alien skies. But perhaps physics itself discourages large-scale expansion by making every journey dangerously expensive, painfully slow, and endlessly vulnerable to failure. Not impossible in the strictest sense, just hostile enough that few civilizations attempt it, or survive it. And still, despite all of these barriers, there remains something deeply human about continuing to imagine the stars anyway. Perhaps because curiosity evolved long before wisdom, or perhaps because somewhere inside every civilization lives the hope that one more breakthrough may still wait ahead. Yet even if humanity someday overcomes radiation, shielding, propulsion, and deep space engineering, another question quietly remains. Can human beings themselves emotionally survive such journeys through darkness? There is a comforting illusion many people carry about machines. We tend to imagine them as tireless, precise, unaffected by emotion, fatigue, or fear. A machine does not grow homesick. It does not panic in darkness. It does not stare through a window longing for oceans or rain or familiar voices. And because of that, it is easy to assume machines may someday solve the problem of interstellar travel for us. Perhaps humans are too fragile for the stars, but machines could continue onward indefinitely, patiently crossing distances that biological life never could. At first, this idea seems reasonable. Machines already survive conditions that would kill humans almost instantly. Robotic spacecraft have crossed the solar system, wandered across Mars, flown beside Saturn's rings, and drifted beyond Pluto into the deep outer darkness. Voyager 1, launched in 1977, is still travelling through interstellar space even now, carrying a faint signal from a civilization that looked very different when the probe first left Earth. When Voyager launched, there were no smartphones, no internet, no digital maps glowing softly in pockets around the world. Humanity had not yet built the International Space Station. Many countries that exist today did not yet exist in their current form, and still, Voyager continues drifting outward, quietly, faithfully, like a bottle floating farther and farther into a black cosmic sea. It is one of humanity's most beautiful achievements, but it is also a reminder of something else. Even our greatest machines are temporary. Voyager survives because engineers built it extraordinarily well, and because it carries systems carefully designed to endure harsh conditions for decades. Yet slowly, year after year, its power fades. Instruments shut down one by one, heat diminishes, communication weakens. Eventually, sometime in the coming years, Voyager's final systems will fall silent forever. Not because of catastrophe, not because it crashed, but because entropy always continues its patient work. That word, entropy, often sounds cold and technical, but in many ways it simply describes the quiet tendency of organized things to gradually fall apart over time. A warm cup of tea cools, metal rusts, paint peels beneath sunlight, memories fade, buildings crack slowly beneath weather and gravity. The universe naturally drifts toward disorder unless energy is continuously used to maintain structure. Life itself is really a long battle against entropy, and so are civilizations. Every road repaired, every roof replaced, every computer updated, every spacecraft maintained. Without constant care, even extraordinary systems slowly degrade. On Earth, this is manageable, because maintenance is everywhere. Human civilization functions like an enormous network of continuous repair. When something breaks, people notice. Tools arrive, replacement parts are manufactured, systems recover. But deep space is different. An interstellar spacecraft travels alone. There are no nearby factories, no emergency rescue ships, no technicians waiting at the next station. Every system aboard the vessel must survive isolation for years, perhaps centuries, possibly far longer. And in that environment, tiny failures become dangerous. A microscopic crack expands slowly through metal after decades of thermal stress. Radiation damages delicate electronics one particle at a time. Data slowly corrupts. Sensors drift slightly out of alignment. Lubricants degrade. Materials become brittle. Not dramatic collapse. Accumulation. Like wind gradually wearing stone smooth over thousands of years. Radiation is especially merciless in this process. Interstellar space is flooded with high-energy particles moving near the speed of light. Many originate from violent cosmic events unimaginably far away. Exploding stars, colliding neutron stars, matter spiraling into black holes. The galaxy is constantly alive with invisible storms. On Earth, we rarely notice because our atmosphere and magnetic field protect us. But outside that protective shell, spacecraft endure continuous bombardment. A single high-energy particle can flip bits inside computer memory, damage circuitry, or slowly weaken electronic systems. Engineers already designed space hardware with extensive redundancy because of this. Important spacecraft systems are often duplicated many times over, allowing backups to take over when failures occur. But redundancy itself increases complexity, and complexity introduces more opportunities for eventual breakdown. This creates a strange paradox. The more advanced and capable an interstellar spacecraft becomes, the more systems it must maintain, and the more vulnerable it may become to long-term degradation. Even artificial intelligence, often imagined as humanity's future representative among the stars, would still depend on physical hardware vulnerable to radiation, heat, and time. A machine mind may not feel loneliness, but its circuits still decay, and over truly enormous spans of time, the universe is astonishingly effective at dismantling fragile arrangements of matter. Imagine a spacecraft attempting to cross large portions of the galaxy. Not years, not decades, thousands of years, perhaps longer. During that time, civilizations on Earth might transform beyond recognition many times over. Languages evolve, continents shift slightly, entire cultures disappear into history. Meanwhile, the spacecraft continues drifting silently through darkness, carrying aging machinery, exposed to relentless cosmic conditions without meaningful maintenance. The scale becomes difficult to emotionally grasp. Human beings often underestimate deep time because our lives are short. A century feels long to us. 1,000 years already feels ancient. But the galaxy operates comfortably on scales far beyond that. Stars live for billions of years. Galaxies rotate over hundreds of millions. The cosmos is patient in ways machines are not. And this may be one of the hidden reasons interstellar expansion becomes so difficult. It is not enough to build a fast ship. You must build a civilization-sized system capable of surviving isolation against entropy for periods longer than most human institutions have ever existed. Even generation ships, giant habitats carrying multiple generations of people between stars, would face this challenge constantly. Every ecosystem aboard would require maintenance, every technological layer would slowly wear down, and future generations born aboard the vessel may no longer fully understand the systems sustaining them. Knowledge itself can erode over time, cultures drift, priorities change, missions lose emotional clarity after centuries. The descendants of travellers might eventually question why the journey began at all. And somewhere inside this realization lies another quiet explanation for the silence of the universe. Maybe civilizations do dream of the stars, maybe many attempt the journey, but perhaps only a tiny fraction survive the immense collision between complexity and deep time. Because the universe does not merely challenge travellers with distance, it challenges them with duration, and duration slowly transforms everything: machines, civilizations, memories, even purpose itself. Yet despite all this, perhaps the most fragile part of any interstellar mission would not be the hardware. It would be the human beings trapped inside it. For all our technology, human beings remain profoundly creatures of Earth. This is easy to forget. We surround ourselves with climate control, artificial lighting, airplanes, satellites, and glowing screens that make civilization feel detached from nature. But beneath all of that, the human body still carries the fingerprints of the planet that shaped it. Every breath you take depends on a very particular atmosphere. Every step depends on gravity pulling gently, downward. Your bones, muscles, inner ear, immune system, and even your sense of balance evolved beneath blue skies, weather patterns, oceans, bacteria, sunlight, seasons, and the steady rhythm of Earth's 24-hour day. Remove those things for long enough, and the body begins to change, sometimes in subtle ways, sometimes in alarming ones. Astronauts already experience this aboard the International Space Station, despite remaining relatively close to Earth. Floating in microgravity for months causes muscles to weaken and bones to lose density because the body no longer experiences the familiar stress of supporting weight. On Earth, simply standing upright constantly reminds the skeleton to remain strong. Gravity quietly trains the body every second of every day. In orbit, that reminder disappears. The body begins adapting to a world where weight no longer matters. Muscles shrink, bones thin, fluids shift upward toward the head, subtly changing vision and pressure inside the skull. Even the heart adjusts because pumping blood upward becomes easier without gravity constantly pulling downward. Astronauts exercise intensely for hours each day simply to slow these effects, not eliminate them, slow them. And these are missions lasting months, not decades. Interstellar travel would magnify these problems enormously. A spacecraft carrying humans between stars might spend years, generations, or even centuries isolated from any planetary environment remotely similar to Earth. The human nervous system has never evolved for such conditions. Neither has the human mind. There is a quiet emotional cost to space that is difficult to measure scientifically. Isolation, not ordinary loneliness, something deeper, a kind of separation from every instinctual comfort the species evolved alongside. No fresh wind, no rain against windows, no forests moving softly in sunlight, no changing seasons, no smell of oceans or soil after storms. Inside an interstellar spacecraft, life would become highly controlled. Artificial air recycled endlessly through machines. Artificial light carefully timed to simulate day and night. Artificial gravity, if available at all, generated mechanically through rotating habitats or continuous acceleration. Everything alive aboard the ship would exist inside a fragile manufactured environment, surrounded by lethal vacuum on all sides. And unlike explorers crossing oceans here on Earth, interstellar travellers could never step outside safely beneath open skies. There would be no beaches waiting at the end of difficult days, no mountains, no rivers, No natural ecosystems beyond the vessel's walls, just machinery, metal, recycled air, and darkness stretching endlessly beyond reinforced windows. Human beings are surprisingly psychological creatures. Our minds respond powerfully to environments even when we pretend otherwise. People living through long winters often experience emotional strain from lack of sunlight. Submarine crews carefully monitor morale during extended underwater missions. Researchers stationed in Antarctica report feelings of detachment, monotony, and emotional fatigue after months isolated in frozen environments. And those people still remain on Earth. They know rescue is possible. They know home still exists nearby. Interstellar travelers would face a far more profound form of isolation. No rescue, no returning quickly, no emergency evacuation, no meaningful real-time conversation with Earth. Even communication itself becomes strangely ghost-like across interstellar distances. A message sent home may take years to arrive. Replies return years later still. Imagine missing someone and waiting a decade for a conversation. Imagine grieving losses long after they happened. Imagine children aboard a generation ship knowing Earth only through recordings, stories, and fading historical memory. At that point, Earth itself might begin feeling mythical, a place spoken about more than remembered. And then there is radiation, one of the most serious biological dangers in deep space. Earth's atmosphere protects life extraordinarily well from cosmic radiation. But beyond that protective cocoon, high-energy particles constantly strike living tissue. Over long periods, radiation increases cancer risk, damages cells, and may affect the nervous system in ways scientists still do not fully understand. Heavy shielding can help, but shielding increases spacecraft mass dramatically, and once again, every solution quietly circles back toward the same problem. Mass requires energy. Energy requires fuel. Fuel increases mass. The cycle returns, again and again, almost like the universe gently refusing to make the journey easy. Some researchers have proposed suspended animation or cryogenic sleep as possible solutions. If travelers could safely sleep through long journeys, perhaps the psychological burden would lessen. But human biology is delicate. Freezing living tissue without damage remains an unsolved challenge. Ice crystals rupture cells. Metabolism becomes difficult to restart safely after extended periods. Nature offers examples of creatures surviving temporary suspended states, but scaling that process to complex human beings remains deeply uncertain. Others imagine uploading human consciousness into machines. Perhaps future civilizations abandon biological bodies entirely and travel as digital minds carried inside durable hardware. It is a fascinating possibility. But even then, the emotional question remains. Would such beings still be recognizably human, or would they become something entirely different? And perhaps this is the deeper realization slowly emerging beneath all these engineering discussions. Interstellar travel is not simply difficult because of rockets or fuel. It is difficult because humans themselves were shaped by a very specific world. Earth is not merely where we happen to live. It is the environment that built us cell by cell over billions of years. Every instinct in your nervous system expects gravity, sunlight, ecosystems, weather, horizons, and a living biosphere filled with familiar rhythms. Take those away long enough, and both body and mind begin drifting into unfamiliar territory. The stars may not simply be far away physically, they may also lie far outside the environmental conditions that biological life naturally belongs to, and yet, despite all this fragility, human beings still dream about the stars. That may be the strangest thing of all. Perhaps intelligence naturally creates longing for horizons beyond itself, or perhaps life, once aware of the universe, cannot help wondering what waits in the darkness beyond its own small island of warmth. Still, if humanity ever truly attempts interstellar migration, it may not happen through small crews enduring years of isolation. The only realistic path may involve something far larger, entire moving civilizations drifting slowly between the stars. As the difficulties of interstellar travel continue unfolding one by one, a quieter idea begins to emerge from the darkness. What if the problem is not reaching another star within a human lifetime? What if humanity simply accepts the slowness? Instead of trying to outrun the limits of physics, perhaps a civilization could drift patiently through them. This is the idea behind generation ships, enormous spacecraft designed not for short missions, but for civilizations, floating worlds carrying entire populations across the deep silence between stars while generations are born, grow old, and die aboard the vessel itself. The people who begin the journey would never see its end. Their grandchildren might not either. Perhaps dozens of generations would live and vanish beneath artificial skies before the ship finally reached another star system. There is something both beautiful and deeply sad about that idea. A city moving endlessly through darkness, children growing up surrounded by metal walls and recycled air, learning about Earth the way modern people learn about ancient kingdoms long vanished into history, as myth, as memory, as something distant and almost unreal. In many ways, generation ships are less like vehicles and more like isolated ecosystems. Everything must survive: air, water, food production, waste recycling, energy systems, medical care, social stability, education, culture itself. A generation ship could not rely on resupply from Earth. There would be no nearby infrastructure waiting to help. Every resource would need to circulate endlessly through carefully balanced systems. A floating world trapped inside its own fragile loop. And Earth already offers reminders of how delicate ecosystems can be. A drought in one region affects food supplies elsewhere. Tiny changes ripple unpredictably through environments. Species disappear, climates shift. Even our own planet, with oceans, forests, and massive self-regulating systems, remains vulnerable to instability. Now imagine compressing an entire civilization into an artificial habitat drifting through interstellar darkness for centuries. The challenge becomes almost overwhelming. Every ecosystem aboard the ship would need extraordinary resilience. Crops must continue growing generation after generation beneath artificial lighting. Water purification systems must function continuously for centuries. Mechanical failures could not simply be repaired using outside supply chains because no outside world exists nearby. The ship itself becomes the entire universe for its inhabitants, and perhaps the most fragile system aboard would not be technological at all. It would be social. Human societies are complicated even on Earth, where vast continents, trade networks, and abundant resources help absorb instability. Civilizations still experience conflict, political collapse, economic failure, cultural fragmentation, and war. Now place a small, isolated population inside a sealed vessel where every disagreement unfolds within the same enclosed environment for generations. No escape, no frontier beyond the walls, no fresh land, no outside contact except delayed messages from a civilization long left behind. The psychological pressure could become enormous. Future generations might question the mission itself. Why continue sacrificing resources and lives for a destination nobody aboard originally chose? The descendants of the travellers may feel little emotional connection to Earth at all. To them, the ship is home. The stars outside are simply distant lights. the mission could begin feeling less like exploration and more like inherited obligation. Cultures evolve surprisingly quickly over long periods of time. Languages drift, values change, stories transform. A generation ship travelling for hundreds or thousands of years might gradually develop entirely new social structures, religions, myths, and identities shaped by isolation inside the vessel. Earth could become a kind of ancestral legend, a lost paradise beneath blue skies and open oceans, and the people aboard might no longer see themselves as Earthlings at all. They may become something culturally distinct, a civilization born between stars rather than on planets. This raises another unsettling possibility. A generation ship may succeed physically, while failing psychologically. The vessel could survive, the ecosystem could survive, but the mission itself could dissolve slowly over time as the population changes emotionally. Perhaps future generations decide to stop the journey entirely. Perhaps political conflicts emerge. Perhaps the knowledge required to maintain critical systems erodes gradually over centuries. Human civilization depends heavily on accumulated expertise. Even today, most people do not personally understand the infrastructure sustaining their daily lives. Electricity grids, satellites, medical systems, and digital networks function because highly specialized knowledge passes continuously between generations. Inside a generation ship, preserving that chain of knowledge becomes essential and difficult. A single prolonged breakdown in educational governance could cascade into catastrophic failure centuries later. The ship might slowly drift into technological decline while still moving endlessly through darkness. There is also the question of scale. A truly viable generation ship might need to be enormous, not merely a spacecraft, but an artificial world large enough to support stable ecosystems and genetically healthy populations over long periods. Some concepts imagine rotating habitats kilometers wide, generating artificial gravity through centrifugal force, forests growing beneath curved ceilings, lakes, farms, residential districts, schools, hospitals, entire miniature civilizations enclosed inside moving metal shells, not explorers visiting the stars, migratory worlds carrying humanity itself through interstellar night. And even then, deep time remains merciless. Materials age, machines fail, radiation accumulates, unexpected biological problems emerge. Over thousands of years, tiny imperfections compound relentlessly. Entropy waits patiently inside every system. The longer the voyage, the greater the risk. And this may quietly explain why large-scale interstellar colonization never appears in reality, despite feeling so common in fiction. The challenge is not simply building a fast enough ship, it is sustaining an entire civilization against isolation, entropy, psychological drift, and deep time itself. A generation ship is less like launching a vehicle, and more like attempting to preserve a fragile moving fragment of civilization across an ocean so enormous that multiple human eras pass before land appears again. And suddenly the stars begin feeling emotionally different once more, not unreachable exactly, but separated by distances so vast that crossing them may require civilizations to transform completely in the process. The travellers who finally arrive may no longer truly resemble the people who departed. Perhaps that is the hidden cost of interstellar migration. Not simply energy, not simply time, but identity itself. And if even generation ships struggle beneath these immense burdens, another realization quietly emerges beside them. Maybe the galaxy is simply too large and too slow for true interstellar empires to ever meaningfully exist. As generation ships drift quietly through the imagination, another realization slowly begins to unfold beside them. Even if humanity someday learns how to survive the journey between stars, another problem still remains waiting in the darkness: communication. Because distance does not only separate bodies, it separates moments, and once civilization spread far enough across space, time itself begins pulling them apart. Here on Earth, modern civilization depends heavily on speed. Messages cross oceans instantly. Financial systems synchronize globally in fractions of a second. Governments respond rapidly to crises unfolding thousands of kilometers away. Families separated by continents still speak face to face through glowing screens carried in pockets. Human civilization feels unified largely because communication is fast. But interstellar distance quietly destroys that unity. The speed of light may feel impossibly fast in everyday life, yet across cosmic scales, even light becomes painfully slow. A message sent from Earth to Proxima Centauri, our nearest neighbouring star system, would take more than 4 years to arrive. A reply would require another 4 years to return. A simple exchange of greetings now stretches across nearly a decade, and that is merely the nearest star. Imagine a human colony orbiting a world 50 light years away. A message announcing a scientific discovery takes half a century to arrive. A response returns 50 years later still. A single conversation now lasts longer than most human lives. Parents send messages to descendants they will never personally meet. Political decisions become impossible to coordinate meaningfully across such enormous delays. By the time information arrives, the original situation may already have changed completely. Wars could end before warnings arrive. Trade agreements become historical documents before negotiations conclude. Entire governments might rise and collapse while distant colonies still wait for updates from Earth. At that point, the idea of a centralized galactic civilization begins quietly unraveling. Not because of rebellion, not because of incompetence, but because the galaxy itself moves too slowly. Human beings often imagine future interstellar societies as expanded versions of earthly empires, vast federations stretching elegantly across thousands of star systems, unified civilizations connected through advanced technology and shared identity. But physics complicates that dream profoundly. A civilization spread across hundreds or thousands of light years would not experience a common present moment. Different regions of the civilization would effectively exist in different centuries relative to one another's information flow. News from distant colonies might already be generations old upon arrival. Cultural trends, languages, political systems, and values would drift independently over time. Even biological evolution could slowly begin separating isolated populations living beneath different stars for thousands of years. The farther civilizations spread, the less synchronized they become, until eventually the idea of one civilization may stop making sense entirely. Instead, interstellar expansion might produce countless isolated descendants, slowly diverging from one another across deep time. Children of the same origin, no longer sharing the same historical rhythm. This creates a strange emotional image of the galaxy. Not a bustling interconnected empire, but an archipelago of lonely worlds, each moving through its own local version of history, connected only by delayed echoes of light. Imagine receiving a message from Earth announcing the outcome of an election, only for the politicians involved to have died generations earlier by the time the message arrives. Imagine falling in love with someone living dozens of light years away, knowing each exchange of words consumes years of waiting. Imagine scientific collaboration unfolding so slowly that entire careers pass between responses. The emotional texture of civilization changes completely under such conditions. Patience would become essential in ways modern humanity can barely imagine. And perhaps this is why fictional faster-than-light communication appears so often in science fiction stories. Without it, interstellar civilization becomes fragmented almost immediately. Not physically fragmented at first, temporally fragmented, separated by time delays so severe that shared experience begins dissolving. Even identity itself becomes difficult to maintain. What does it mean to belong to the same civilization if your descendants experience history at entirely different speeds from people elsewhere? Earth today feels globally connected because information moves almost instantly. Shared events create shared memory. Humanity watches the same moments unfold together. But in an interstellar civilization, simultaneity itself begins disappearing. A colony 100 light-years away effectively lives inside a different informational universe. And over centuries, those informational separations accumulate, slowly, quietly, like continental drift. This may also explain why galactic empires feel strangely absent from reality, despite appearing constantly in fiction. The universe may simply discourage centralized expansion, not violently, not dramatically, just through relentless delay. Every additional light year stretches communication thinner, every century increases cultural divergence further, until eventually the stars no longer feel politically connected at all, only historically related. And perhaps there is something strangely peaceful about that realization. The galaxy may contain civilizations scattered everywhere, yet none capable of forming vast unified empires dominating the stars. Distance protects worlds from one another almost automatically. The same physics preventing easy exploration may also prevent large-scale conquest. Earth itself may remain safe, partly because the universe is too large and too slow for rapid interstellar expansion to function meaningfully. The night sky feels empty, partly because the cosmos resists synchronization. Civilizations may bloom around distant suns, rise, wonder, dream, struggle, and disappear, all without ever overlapping in time closely enough to truly encounter one another, like candles briefly glowing in separate windows across an unimaginably large dark landscape, visible perhaps, but never truly near. And somewhere within that realization, the famous silence of the universe begins feeling slightly different, less mysterious, less paradoxical. Because perhaps the cosmos is not empty at all. Perhaps it is simply fragmented by time itself. For many decades, one question has quietly haunted modern astronomy. If the universe is so enormous, where is everybody? The question became famous through physicist Enrico Fermi during a casual conversation in the middle of the 20th century. The galaxy contains hundreds of billions of stars. Many of those stars are older than the Sun. Around many of them orbit planets. And across the vast age of cosmic history, it seems statistically difficult to imagine that humanity is the only civilization ever to emerge. So why does the universe appear so silent? No giant alien structures surrounding stars, no visible galactic empires, no clear signals, no visitors arriving from ancient civilizations millions of years older than ours. Just darkness, just distance, just the quiet drifting of galaxies through space. This puzzle became known as the Fermi paradox, and for years people proposed dramatic explanations. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves before spreading outward. Perhaps advanced beings deliberately hide. Perhaps humanity lives inside some kind of cosmic wilderness, where older civilizations avoid interference. These possibilities are fascinating, but tonight another explanation quietly emerges from everything we've explored so far. What if the silence is not mysterious at all? What if the universe simply makes large-scale interstellar expansion extraordinarily difficult? Not impossible in every absolute sense, but slow enough, expensive enough, dangerous enough, and fragmented enough that civilizations remain mostly trapped within their own local regions of space. When viewed this way, the Fermi paradox begins softening into something less paradoxical. Imagine countless islands scattered across a dark ocean larger than comprehension itself. Each island develops its own civilization, its own stories, its own science, its own dreams about crossing the water. But the ocean between them is so immense and the storms so severe that meaningful travel rarely succeeds. The islands still exist, they simply remain separated. Perhaps the galaxy works the same way. There may indeed be civilizations scattered throughout the Milky Way, some younger than humanity, some unimaginably older, some perhaps already vanished long before Earth even formed. But interstellar distance prevents them from forming coherent galaxy-wide civilizations. Every attempt at expansion collides with the same barriers: relativity, energy, entropy, radiation, communication delay, deep time. Again and again, the universe quietly resists synchronization. And once these limits are taken seriously, the expectation of seeing obvious galactic empires begins fading naturally. Because colonizing a galaxy is not like colonizing a continent. On Earth, oceans separate civilizations by days or months of travel. In space, the distances are measured in years, centuries, or longer even for communication itself. The Milky Way is roughly 100,000 light-years across. Even if a civilization expanded steadily from star to star, the process could require immense stretches of time. Entire branches of the civilization would drift culturally and biologically during the expansion itself. And perhaps many civilizations simply decide the cost is not worth paying. This is another possibility often overlooked in older visions of interstellar conquest. Advanced intelligence may not automatically desire endless physical expansion. Human civilization often assumes growth outward is inevitable because much of human history involved territorial expansion across Earth. But future civilizations may develop entirely different priorities: virtual realities, artificial worlds, digital existence, deep scientific exploration without physical migration. A sufficiently advanced civilization might discover that transmitting information is vastly easier than transporting biological life across interstellar distances. Why move fragile bodies between stars when knowledge itself can travel at light speed? Why build empires across thousands of worlds when local systems already contain more energy and resources than civilizations could meaningfully consume? Perhaps mature civilizations become quieter rather than louder, more inward, more contemplative, not because they lack power, but because physics encourages efficiency over expansion. And suddenly the silence of the galaxy begins feeling less eerie, not evidence of absence, evidence of distance. There is also the problem of overlap. The universe is ancient, but civilizations may still be brief relative to cosmic timescales. Human technological civilization has existed for only a tiny fraction of Earth's history. Radio communication itself has existed for barely more than a century. On cosmic scales, that is less like a civilization announcing itself and more like a single spark briefly appearing in darkness. Another civilization could have risen and vanished millions of years ago before Earth even evolved complex animals. Others may emerge millions of years from now after humanity is gone. Two civilizations may exist in the same galaxy, yet never overlap closely enough in both space and time to encounter one another. Like ships passing silently in fog centuries apart. And even if signals are transmitted, they weaken across distance. Radio waves spread outward and fade. Detecting them requires extraordinary sensitivity and good timing. The galaxy may not be silent. It may simply be whispering across impossible distances. This perspective transforms the emotional tone of the Fermi paradox completely. Instead of imagining a hostile or empty universe, we begin imagining a cosmos filled with isolated pockets of awareness unable to easily bridge the spaces between them. Civilizations staring upward beneath alien skies, wondering the same things we wonder, listening carefully for replies that may take centuries to arrive, if they arrive at all. And perhaps somewhere tonight, around another distant star, another species is also lying awake beneath dim artificial lights, asking why the universe feels so quiet despite containing so many stars. Maybe they have reached the same conclusion we are slowly approaching now. That intelligence is not enough to conquer cosmic scale, that physics itself shapes the destiny of civilizations, that the universe may naturally produce islands of awareness separated by distances too vast and timescales too deep for meaningful physical contact to occur often. And perhaps that is not tragic. Perhaps it is simply the architecture of reality. The stars remain visible to one another, but not necessarily reachable. Still, human imagination rarely accepts limits quietly, and throughout history, whenever reality appeared to place barriers in the way, people continued searching for loopholes, shortcuts, hidden paths, ways to escape the ordinary rules governing motion and distance. So naturally, physicists eventually began asking an extraordinary question. What if space itself could somehow bend? As the silence of the universe begins feeling less mysterious, another thought naturally appears beside it. Perhaps someone listening to all of this might quietly wonder, what if civilizations simply become advanced enough? After all, human history is filled with barriers that once seemed permanent. People once believed oceans were uncrossable, then ships improved, mountains blocked movement, roads and tunnels appeared. Human flight sounded impossible until engineering slowly transformed imagination into reality. So perhaps relativity, energy, and interstellar distance are simply temporary obstacles, waiting for sufficiently advanced technology to overcome them. It is a reasonable thought, and in many ways science itself encourages that optimism. Again and again, intelligence has expanded what humanity can accomplish. But there is an important distinction hidden underneath all technological progress. Some barriers are engineering problems, others are woven directly into the laws of physics themselves. That distinction matters enormously. A bird cannot cross an ocean easily. An airplane can. That is an engineering solution. Human beings cannot breathe underwater naturally. Submarines solve that limitation. Again, engineering. But no machine ever escapes gravity completely. Gravity shapes every orbit, every trajectory, every movement of stars and galaxies themselves. Technology negotiates with physical law. It does not erase it. And this is where interstellar travel becomes fundamentally different from many earlier human achievements. The barriers involved are not merely practical inconveniences awaiting clever design. They emerge from the structure of reality itself. The speed of light is not simply a current technological limit like the sound barrier once was for airplanes. Relativity predicts deep consequences for any object approaching that speed. Energy requirements rise enormously. Time behaves differently. Causality, the relationship between cause and effect, becomes entangled with motion itself. These are not flaws in current engines, they're properties of space-time, and throughout more than a century of experimental testing, relativity has continued proving astonishingly accurate. Again and again, nature behaves exactly as Einstein's theories predict. This does not mean future discoveries are impossible. Science always remains open to refinement and deeper understanding. But there is a profound difference between. We have not solved this yet, and the universe may fundamentally resist this entirely. That distinction is easy to blur in imagination, especially because advanced technology often feels almost magical when viewed from a distance. To someone living 1,000 years ago, modern civilization would appear impossible. Satellites orbit overhead invisibly, voices travel instantly across oceans. Tiny devices contain libraries larger than ancient kingdoms could ever gather physically. And yet all these technologies still obey the same physical laws governing stones, stars, rivers, and planets. The laws themselves never disappeared. Humanity simply learned how to work within them more effectively. This is why many physicists remain cautious about dreams of limitless, interstellar expansion. Advanced civilizations may indeed achieve extraordinary things. They may harness fusion power, build vast artificial habitats, engineer sophisticated artificial intelligence, extend lifespans dramatically, manipulate matter with incredible precision. But none of those automatically remove the deeper constraints imposed by relativity, thermodynamics, entropy, and finite energy. Intelligence does not create infinite resources. It does not eliminate time. It does not erase distance. And perhaps most importantly, it does not force the universe to behave differently simply because civilizations desire it to. There is something quietly humbling about that realization. Human beings often imagine intelligence as a kind of cosmic mastery. The smarter a civilization becomes, the more powerful it grows. But physics remains indifferent to ambition. Stars collapse whether civilizations approve or not. Entropy continues patiently unfolding. Galaxies drift apart. Light travels at the speed it travels. The universe does not negotiate emotionally. It simply is. And perhaps this explains why many scientific discussions about advanced alien civilizations become surprisingly restrained once physical laws are considered seriously. Science fiction often imagines ancient species effortlessly crossing galaxies, controlling time, or ignoring relativistic limitations entirely. But real physics offers surprisingly few loopholes. Again and again, shortcuts create new problems. Move near light speed, and energy requirements explode. Attempt faster than light travel, and causality itself becomes unstable. Build larger systems, and entropy slowly erodes them over time. The deeper we look into reality, the more interconnected the limits appear, like threads woven tightly together inside the fabric of existence. There is also another subtle point often overlooked in discussions about advanced civilizations. A civilization does not become infinitely capable simply by surviving longer. Even extraordinarily advanced societies must still allocate resources, manage risk, and make decisions about what is worthwhile. Interstellar expansion may remain physically possible in principle, while becoming economically, energetically, and socially unreasonable in practice. A civilization millions of years old might still conclude that spreading physically across thousands of stars offers too little benefit relative to the immense cost, especially if communication delays permanently fragment distant colonies anyway. Perhaps advanced civilizations become less interested in expansion over time, not more. Maturity may produce caution rather than conquest, efficiency rather than endless growth, observation rather than domination. This possibility changes the emotional feeling of the cosmos again. The silence of the universe may not indicate failure, it may indicate restraint. Civilizations quietly adapting themselves to the deep structure of reality rather than endlessly trying to overpower it. And perhaps humanity itself will eventually face that same choice, not whether the stars are beautiful enough to reach, but whether crossing the darkness physically is truly the wisest use of intelligence at all. Still, even within these limits, the human imagination continues searching for pathways through the impossible, because there remains one final possibility difficult to resist. If moving through space itself is too difficult, perhaps space could somehow be bent instead. For as long as human beings have encountered limits, we have also imagined shortcuts. A mountain appears, and eventually someone searches for a tunnel. An ocean blocks the horizon, and someone begins building ships. So it is perhaps inevitable that once physicists realized the stars were separated by nearly impossible distances, imagination immediately began searching for hidden pathways through space-time itself. And among all the strange ideas ever proposed in theoretical physics, few are as hauntingly beautiful as wormholes. The name itself sounds almost organic, like tunnels carved quietly through the roots of the universe. At first glance, wormholes seem less like science and more like mythology, invisible bridges connecting distant regions of space, shortcuts through reality itself, pathways allowing travellers to cross enormous distances without actually moving faster than light. And strangely enough, modern physics does allow the mathematics for such structures to exist, not proven structures, not observed ones, but mathematical possibilities emerging naturally from Einstein's description of gravity and space-time. To understand the basic idea, it helps to imagine space differently. In everyday life, we experience space as flat and straightforward. You walk across a room in a straight line. A car drives down a highway. Distance feels fixed and ordinary. But relativity revealed that space is not rigid. Mass and energy bend it, stretch it, curve it. A planet does not orbit the sun because an invisible force reaches outward like a rope pulling it around. Instead, the sun curves space-time around itself, and Earth simply follows that curvature through space. Reality behaves less like a static stage and more like a flexible fabric. And once physicists realized space-time could bend, another question naturally emerged. Could it fold? Imagine drawing two dots on opposite sides of a sheet of paper. Under ordinary conditions, travelling between them requires crossing the entire distance across the page. But if you gently fold the paper until the dots touch, the journey suddenly becomes tiny. Not because the traveller moved faster across the paper, but because the geometry itself changed. That is the emotional intuition behind wormholes, not outrunning light, shortening the path, a tunnel through curved space-time connecting distant regions that would otherwise require enormous journeys. It is a deeply seductive idea, because it appears to bypass many of the cruelest barriers of interstellar travel all at once. Distance shrinks, travel times collapse, relativity remains technically unbroken because nothing locally exceeds light speed. Instead, space itself provides the shortcut. In some versions of the concept, a traveller entering a wormhole near Earth might emerge almost instantly, near another star many light-years away. The galaxy suddenly becomes intimate, crossable. The dream of interstellar civilization returns once more, and yet, almost immediately, reality begins resisting again. Because while the equations of general relativity allow wormhole-like structures mathematically, keeping them open appears extraordinarily difficult. A natural wormhole would likely collapse almost instantly, like a tunnel caving in faster than anything could pass through it. To stabilize the opening, physicists believe some form of exotic matter may be required, matter with unusual properties, unlike anything humans have ever observed directly in large quantities. In simplified terms, this exotic matter would need to possess negative energy density, a phrase that sounds abstract and technical, but emotionally means something almost impossible, a form of energy behaving opposite to ordinary matter. Instead of reinforcing gravity, it would counteract it. Instead of collapsing the tunnel, it would help hold space-time open. Small quantum effects resembling negative energy do appear in certain physical situations, but the quantities involved are tiny, delicate, and extremely difficult to scale into anything remotely practical. No one currently knows whether stable, human-traversable wormholes could actually exist in reality. And even if they could, new problems quickly appear. Wormholes may introduce severe instability. Radiation could build catastrophically inside them. Tiny disturbances might trigger collapse. Quantum effects may destroy the structure entirely. And perhaps strangest of all, wormholes may create problems with causality itself. Because if two distant regions of space-time become directly connected, the distinction between before and after can begin behaving in unsettling ways. Under certain conditions, wormholes may theoretically allow forms of backward time travel or paradoxical causal loops. And whenever physics starts producing paradoxes, scientists become cautious, very cautious, because paradoxes often suggest one of two possibilities. Either our understanding is incomplete, or nature itself prevents the situation from occurring physically. Again and again, the universe seems strangely protective of causality, the simple idea that causes happen before effects. Reality appears structured in ways that preserve consistency, and this creates a recurring emotional pattern throughout interstellar physics. Every apparent shortcut reveals deeper complications waiting underneath, like discovering hidden currents beneath calm water. Still, wormholes remain scientifically valuable to explore, not because physicists necessarily expect humanity to build them soon, or ever, but because studying extreme possibilities teaches us something profound about space-time itself. Wormholes force scientists to confront deep questions. What is space, really? Can geometry become dynamic enough to reconnect distant regions? Are distance and locality fundamental, or emergent properties of something deeper? In that sense, wormholes are not merely speculative transportation concepts. They are windows into the hidden architecture of reality, and perhaps this is why they continue capturing human imagination so powerfully. Wormholes transform the universe emotionally. The stars no longer feel permanently separated. Instead, they become rooms connected by invisible doors hidden somewhere inside the fabric of space-time. It is a beautiful thought, a hopeful thought, but at least for now, still deeply uncertain. And so humanity's search for escape routes continues, because if tunnels through space remain unstable, perhaps there is another possibility still waiting quietly in the mathematics. What if a spacecraft never moved through space faster than light at all, but instead carried space-time itself along for the journey? Even after relativity placed enormous barriers between the stars, human imagination continued searching for ways around them. And perhaps the most famous attempt emerged from a wonderfully strange question. What if a spacecraft never actually moved through space faster than light? What if space itself moved instead? At first, this sounds almost like wordplay, a clever trick hiding inside language. But in the 1990s, physicist Miguel Alcubierre proposed a mathematical solution within Einstein's equations, suggesting something extraordinary. In theory, space-time itself might be manipulated, not broken, not escaped, distorted. The idea became known as the Alcubierre warp drive, and emotionally it feels very different from ordinary propulsion. A conventional spacecraft pushes itself through space like a boat crossing water. The faster it travels, the more energy and resistance become overwhelming. But a warp drive imagines something stranger. Instead of moving the ship rapidly through space-time itself expands behind the vessel and contracts ahead of it. The spacecraft sits inside a kind of bubble. Locally, it remains almost still relative to its immediate surroundings. Inside the bubble, travellers might feel little acceleration at all, but the bubble itself moves because space-time changes shape around it. A gentle analogy might be this. Imagine standing on a moving walkway inside an airport. You're not sprinting across the floor yourself. Instead, the floor carries you forward. Now imagine the floor itself bending and sliding beneath reality. The destination comes closer, not because you crossed the distance conventionally, but because space-time rearranged the distance around you. In principle, such a bubble could move effectively faster than light without violating relativity locally. Nothing inside the bubble outruns light in its immediate region of space-time. Again, the loophole appears elegant. The universe seems almost briefly negotiable, and unsurprisingly, the concept captured enormous public imagination. Science fiction had already dreamed of warp drives for generations. Suddenly, theoretical physics appeared to whisper that perhaps such ideas were not entirely fantasy after all. The stars felt close again, reachable again, but as often happens in deep physics, the first glimpse of possibility was followed by a growing mountain of complications. The original Alcubierre proposal required enormous amounts of negative energy, not simply large amounts, absurd amounts. Early calculations suggested energy comparable to the mass energy of entire planets or stars might be necessary just to form a microscopic warp bubble. Later refinements reduced those estimates somewhat, but the requirements remained staggeringly extreme, and once again, negative energy enters the story. The same strange ingredient haunting wormhole theories appears here too. Physics permits certain tiny quantum effects, resembling negative energy under highly specialized conditions, but no known mechanism allows humanity to generate or control the vast quantities apparently required for warp travel. The mathematics remains fascinating, the engineering remains almost unimaginable, and even if energy problems could somehow be solved, deeper issues begin emerging underneath. One of the most troubling involves causality. Causality is one of those words that sounds technical until you realize how fundamental it truly is. It simply describes the ordinary flow of reality. Causes happen before effects. You drop a glass, then it shatters. You send a message, then someone receives it. The order matters. Without causality, reality itself becomes unstable and paradoxical, and faster-than-light motion creates deeply uncomfortable tensions with that structure. Because according to relativity, if information or objects travel faster than light under certain conditions, different observers may disagree about the order of events. One observer may see a message sent before it is received. Another may perceive the reply arriving before the original message was even transmitted. The distinction between past and future begins blurring in unsettling ways. And this is not merely philosophical confusion. It creates paradoxes. If information can travel backward in time relative to some observers, strange loops emerge. A civilization might theoretically receive warnings before disasters occur. Messages could influence events that have not yet happened from another perspective. The universe begins resembling a story tangled in its own pages. Physicists become deeply cautious whenever such paradoxes appear, because nature consistently seems organized around preserving causal consistency. Reality protects sequence, protects order, protects the difference between before and after. And again, theoretical shortcuts toward faster-than-light travel seem to threaten that structure. This has led some scientists to suspect that hidden physical mechanisms may always prevent such systems from functioning in practice, even if mathematical solutions exist on paper. The equations permit beautiful possibilities. Reality may quietly forbid them, and perhaps this pattern itself is meaningful. Every time civilizations imagine escaping cosmic distance through some grand loophole, the universe responds with deeper constraints hidden underneath. As though space-time possesses a kind of structural integrity it does not easily allow intelligence to violate. This does not make warp drive research pointless. Far from it. Studying these ideas pushes physics toward deeper understanding. Questions about space-time geometry, quantum fields, gravity and causality all become clearer when scientists explore the extreme edges of possibility. Even failed ideas illuminate reality. Sometimes, especially failed ideas. And emotionally, warp drives reveal something important about humanity itself. The refusal to stop imagining pathways through darkness. Again and again, intelligence presses gently against the boundaries of the universe, asking, "Is there another way?" That curiosity may be one of the most beautiful qualities conscious life possesses. Still, the deeper physicists explore these concepts, the more reality appears reluctant to permit unlimited movement through the cosmos. Not violently, not cruelly, just consistently. The structure of space-time keeps reasserting itself. Distance matters, time matters, energy matters, causality matters. And perhaps the most unsettling realization of all is that even if civilization solved every local engineering problem imaginable, the universe itself may still continue expanding beyond their reach. Galaxies drifting farther apart, regions of space becoming permanently inaccessible, the cosmos slowly stretching itself wider and wider over unimaginable spans of time, as though reality itself were quietly increasing the distance between its islands of light. As the dream of warp drives and space-time shortcuts slowly fades back into uncertainty, another realization begins rising from the darkness behind it. Even if humanity solved propulsion, even if radiation, energy, and relativity somehow became manageable, even if civilizations learned to survive for millions of years, the universe itself would still continue changing underneath them, because the cosmos is not static, it is expanding, and perhaps the strangest part of all is that the expansion is accelerating. For most of human history, people imagined space as fixed and eternal. Stars appeared frozen against the night sky like distant lanterns suspended above the world. But during the 20th century, astronomers discovered something extraordinary. Galaxies are moving away from one another, not because they are flying through space like debris after an explosion, but because space itself is stretching. The universe behaves less like objects drifting through emptiness, and more like the surface of an inflating fabric carrying galaxies apart as it expands. A gentle way to imagine it is to picture small dots drawn onto a balloon. As the balloon inflates, every dot moves farther away from every other dot. No single dot sits at the center of the expansion. The distances increase because the surface itself stretches. Our universe behaves similarly on enormous scales, and the farther away galaxies are, the faster they appear to recede from us. This does not violate relativity because the galaxies are not necessarily traveling through local space faster than light. Instead, space-time itself expands between them. distance grows naturally over time. For nearby galaxies, gravity still matters strongly enough to hold structures together. The Milky Way and Andromeda, for example, are actually moving toward one another and will likely merge billions of years from now. But on larger scales, expansion dominates. Galaxies drift apart slowly, patiently, relentlessly. And for a long time, scientists assumed gravity would gradually slow this expansion over cosmic history. That seemed intuitive enough. Gravity pulls matter together, so eventually the expansion should weaken. But in the late 20th century, astronomers discovered something deeply surprising. The expansion of the universe is speeding up. Some unknown process, often associated with what physicists call dark energy, appears to be pushing distant galaxies apart faster and faster over time. And this realization carries enormous consequences for interstellar civilization, because it means parts of the universe are gradually becoming unreachable forever. Not technologically unreachable, physically unreachable. There are galaxies so distant that even light leaving them today will never reach us in the far future, because the expansion of space continually stretches the distance faster than the light can close it. The universe itself slowly carries those regions away, like islands drifting apart on an endless dark sea. This creates something known as a cosmic horizon. Not a wall, not an edge, more like a limit to future connection. Beyond certain distances, causal contact itself becomes impossible over sufficient spans of time. Signals cannot bridge the growing separation forever. Travel cannot overcome the stretching fast enough. Entire regions of reality slowly disappear into permanent inaccessibility. There is something strangely emotional about this idea. At night, when we look into the sky, many of the galaxies visible through telescopes are not simply far away. They are temporary companions. In the unimaginably distant future, cosmic expansion may carry many of them beyond visibility entirely. Future civilizations living trillions of years from now may look outward and see a much darker universe than we do today. Most galaxies will already have slipped beyond their observable horizon. The cosmos itself slowly erases its own visible structure over deep time, and suddenly the dream of galactic expansion changes emotionally once again. The universe no longer feels merely difficult to cross. It begins feeling actively dispersive, reality itself increasing the separation between islands of awareness. This has led some physicists and philosophers toward a profound possibility. Perhaps the universe is not naturally structured for empire. Perhaps large-scale cosmic civilization was never the expected outcome of intelligence at all, not because life is weak, not because civilizations are doomed, but because space-time itself encourages locality, small clusters, nearby relationships, isolated systems loosely connected by light. Again and again, the structure of reality seems to favor fragmentation over synchronization. The farther civilizations attempt to spread, the more communication delays grow, energy demands rise, entropy accumulates, cultures diverge, and cosmic expansion widens the distances further. Still, the architecture of the universe quietly resists total connectedness, and perhaps this explains why the night sky feels simultaneously full and empty at the same time. The stars are everywhere. But meaningful contact may remain extraordinarily rare, not forbidden, just stretched thin across scales too immense for civilizations to easily overcome. There is also something unexpectedly humbling in this realization. Human beings often imagine intelligence as a force destined to dominate nature. Stories of conquest and expansion appear throughout history, projecting outward into science fiction, visions of galactic empires spreading endlessly across the stars. But the universe may not reward endless expansion. It may instead reward understanding, adaptation, patience. Perhaps the deepest achievement of intelligence is not conquering space-time, but learning how to exist meaningfully within its limits. And if that is true, then the silence of the cosmos begins feeling less tragic, more contemplative. Civilizations may exist throughout the galaxy and beyond, each living beneath its own sky, studying its own stars, building its own stories, while remaining permanently separated by the expanding geometry of reality itself. Not enemies, not rivals, just distant fellow travellers carried apart by cosmic time. And perhaps that realization changes the emotional meaning of exploration entirely. Maybe the purpose of looking outward was never ownership, never conquest, never empire. Maybe it was simply connection, a brief awareness that somewhere beyond the darkness, other islands of consciousness may also exist, even if the distances between them can never fully close, and if physical journeys across the cosmos remain so profoundly difficult. Perhaps another form of connection becomes more important than ever. Not moving bodies through space, but sending signals through the dark. After wandering through so many barriers, distance, relativity, radiation, entropy, and the expanding fabric of the universe itself, it becomes tempting to imagine the cosmos as hopelessly disconnected. A vast darkness filled with unreachable lights, civilizations isolated forever inside their own small islands of warmth. And yet, there is another way to think about connection, a quieter way. Because perhaps physical travel was never the most important form of contact to begin with. Long before human beings crossed oceans, ideas already travelled between minds, stories survived across generations, songs outlived the people who first sang them, knowledge moved farther than bodies ever could. Even now, much of human civilization depends less on moving people and more on moving information. A scientist in one country sends discoveries instantly across the world. Music written decades ago still reaches new listeners. Voices survive in recordings long after the speakers themselves are gone. Information has a strange kind of endurance, and on cosmic scales, information may matter far more than transportation. Because while moving spacecraft between stars requires enormous energy and terrifying engineering, sending signals through space is comparatively gentle. A radio transmission weighs almost nothing. Light itself travels naturally at the fastest speed the universe allows. No fuel tanks carrying mountains of propellant. No fragile ecosystems trapped inside metal shells. Just patterns crossing darkness. In many ways, this realization quietly transforms the emotional meaning of interstellar civilization. Perhaps advanced societies do not expand physically across galaxies because they do not need to. Perhaps communication itself becomes the true architecture of cosmic connection. This idea lies at the heart of projects like SETI, the search for extraterrestrial intelligence. For decades, scientists have listened carefully to the sky using radio telescopes, searching for patterns that might reveal intelligent origin. Not random cosmic noise, but structured signals carrying evidence of thought. The search itself is wonderfully humble. Humanity is not launching fleets into the stars, it is listening, patiently, quietly, like someone standing beside a dark ocean at night waiting for a distant lighthouse to answer. And perhaps that image captures something important about the universe. Maybe civilizations are less like conquering empires and more like scattered lights across enormous distances, unable to physically reach one another easily, but still capable of exchanging small fragments of awareness through signals drifting patiently across space-time. A radio transmission from Earth already expands outward into the galaxy at light speed. Old television broadcasts, radar pulses, and communication signals continue moving silently through space long after leaving our planet. Somewhere, many light years away, those faint echoes of humanity are still travelling. Tiny traces of our existence crossing darkness long after the original moments have passed. There is something strangely beautiful about that. A child laughing in an old television broadcast. A human voice speaking into a microphone decades ago. Music once played casually in a studio. All of it now drifting outward among the stars. And perhaps other civilizations are doing the same, sending signals, mathematics, greetings, fragments of culture and curiosity carried by light. Not armies, not colonies, just information. Of course, even communication across interstellar distances remains slow. A message to a civilization 100 light-years away still requires a century to arrive. Their response would take another century to return. An ordinary conversation becomes a multi-generational exchange. Questions asked by one civilization may only be answered by descendants many decades later. And yet, compared to the near impossibility of transporting living beings physically across such distances, signals remain astonishingly efficient. Information may ultimately become the natural language of cosmic civilization. Not physical proximity, not empire, but awareness. There is also another subtle possibility hidden inside this idea. Civilizations themselves may not survive forever, but their signals might. A species could vanish long before its transmissions finish crossing the galaxy. In that sense, radio signals become a kind of temporal echo. Ghosts of civilizations continuing to move through space after the original culture has disappeared. Humanity itself may someday become silent, while traces of our broadcasts continue drifting outward for thousands or millions of years. Tiny ripples of consciousness expanding through darkness. This changes the emotional feeling of the Fermi paradox once again. Maybe the galaxy is not silent because nobody exists. Maybe it is filled with overlapping echoes, ancient signals, fading transmissions, brief flashes of awareness crossing impossible distances. The challenge is not necessarily absence. It is listening carefully enough and patiently enough. There is something deeply moving about the idea that civilizations separated forever, physically, may still share knowledge across time through light itself. A species around another star might never touch Earth, never walk beneath our oceans or mountains, never shake human hands, yet they may still learn our mathematics, hear our music, understand our science, know that we existed, and perhaps we could know the same about them. In this way, the universe begins feeling less lonely, not crowded in the ordinary sense, but threaded together faintly by signals moving through darkness like glowing threads stretched across an enormous cosmic tapestry. And maybe that is enough. Maybe intelligence does not need to conquer the galaxy to matter. Maybe simply becoming aware of one another across the silence is already extraordinary. The universe may resist physical closeness, while still permitting connection through knowledge. A softer form of contact, one based not on ownership or expansion, but on recognition. And perhaps, somewhere tonight, another civilization is also turning giant instruments toward the stars, listening carefully through static, wondering whether anyone else is out there beneath the same immense cosmic night. By this point in our journey through the cosmos, the silence of the universe may begin feeling different than it did at the beginning. At first, silence can feel unsettling, empty, like standing alone in a dark forest waiting for an answer that never comes. But after wandering through relativity, distance, entropy, and the immense slowness of space-time, another interpretation begins to emerge softly from the darkness. Maybe nobody's coming because nobody can. Not easily, not quickly, not without sacrificing extraordinary amounts of energy, time, and separation from their own worlds. And if that is true, then perhaps the galaxy is not empty at all. Perhaps it is quietly listening. There is something strangely intimate about that possibility. Imagine civilizations scattered across the Milky Way like distant campfires, glowing across an enormous nighttime landscape, each one surrounded by its own history, languages, fears, discoveries, music, and dreams. Each one looking outward beneath alien skies, wondering whether awareness exists anywhere beyond their own small island of light. Some may live beneath red dwarf stars glowing dimly for trillions of years. Others may orbit worlds with twin suns casting long, overlapping shadows across oceans unfamiliar to human imagination. Some civilizations may be ancient beyond comprehension. Others may only just now be discovering electricity, mathematics, or radio, and perhaps nearly all of them eventually confront the same realization humanity is beginning to face. The universe is not merely large, it is patient, painfully patient. The distances between stars are not obstacles crossed in hours or days. They are measured in years, centuries, and generations. Even light itself requires enormous spans of time to move between worlds. And because of that, intelligent life may naturally evolve into something more contemplative than expansive, less focused on conquest, more focused on listening. Perhaps advanced civilizations eventually understand that physically reaching one another is extraordinarily rare, while awareness itself remains possible through signals and observation. The galaxy may contain countless observers quietly studying the same stars from impossibly distant shores, separated physically, connected faintly through knowledge. This possibility transforms the emotional feeling of cosmic loneliness. Loneliness usually hurts because it feels singular. To feel alone is to imagine separation as unique to yourself. But cosmic isolation may be universal. Every civilization may stand beneath the same impossible distances. Every species may eventually discover the same relativistic barriers and energy limits. Every intelligence may look outward hoping for connection while realizing how difficult true contact becomes across cosmic scales. And strangely, there is comfort in shared isolation, a kind of quiet solidarity between distant minds that may never meet. Human beings already experience small versions of this feeling here on Earth. Someone awake late at night in one country may never meet another person reading beneath a lamp on the opposite side of the planet. Yet there is still a subtle emotional awareness that both exist beneath the same sky. Now expand that feeling across the galaxy. Perhaps somewhere tonight, another civilization is also sitting beside enormous listening instruments, patiently searching radio static for patterns carrying evidence of thought. Perhaps another species has already detected Earth's faint technological whispers and is slowly debating what they mean. Perhaps signals are already moving between civilizations so slowly that neither side yet realizes contact has begun. The galaxy may not be silent in the ordinary sense. It may simply speak too slowly for impatient creatures. There is also another deeply humbling possibility. Humanity may not be especially early or especially late. Civilizations may emerge throughout cosmic history like brief moments of awareness, flickering against immense darkness. Some overlap slightly, others miss one another entirely by millions of years, but all of them inherit the same universe, the same speed of light, the same space-time, the same deep separation between stars. Again and again, reality shapes intelligence into local islands surrounded by enormous distance, not through hostility, just through scale. and perhaps this changes the meaning of intelligence itself. Popular imagination often treats intelligence as a force destined to dominate the cosmos. Science fiction stories overflow with galaxy-spanning empires, civilizations bending reality to their will, species conquering stars endlessly outward. But the actual universe may encourage something quieter: observation, patience, careful listening, awareness without ownership. Maybe the mature response to cosmic scale is not expansion, but humility, not silence born from fear, silence born from understanding. There is something beautiful about that thought. Civilizations scattered across darkness not as rivals, but as fellow witnesses to the same vast reality, each one carrying its own fragile pocket of consciousness through time, each one staring upward with curiosity despite the overwhelming scale surrounding them. And perhaps the greatest achievement of intelligence is not escaping the limits of the universe, but remaining capable of wonder within them. Even now, here on Earth, giant radio telescopes continue turning slowly beneath the night sky. Scientists continue listening patiently through oceans of static. Human beings continue sending probes outward carrying music, mathematics, and images of our world. Not because success is guaranteed, but because curiosity itself seems deeply woven into conscious life. The desire to know whether anyone else is out there may survive even when the odds feel impossibly small. And perhaps that desire matters more than conquest ever could. Because conquest ends, empires fade. But the act of reaching outward, even gently, even uncertainly, reveals something profound about intelligence itself. A refusal to remain emotionally closed inside one small world. Maybe no civilization ever truly crosses the galaxy physically. Maybe the stars remain forever distant, and yet, across all that darkness, signals still travel, thoughts still travel, questions still travel, like tiny lanterns drifting slowly across an endless sea at night, and perhaps somewhere, impossibly far away, another mind is watching those distant lights move through the dark, wondering who first lit them. As our long journey through the darkness between stars begins to settle softly into the distance, one final realization quietly remains. Perhaps the universe was never meant to be conquered. For centuries, human history has often treated exploration as a kind of expansion. New oceans crossed, new continents mapped, new frontiers claimed. Movement became tied to ownership, progress, and control. And when humanity first began dreaming seriously about the stars, many imagined the cosmos unfolding in the same way. Galactic civilizations, interstellar empires, countless worlds connected beneath one vast network of expansion, stretching endlessly outward through space. But the deeper physics reveals itself, the stranger that dream begins to feel. Again and again, the universe resists simplification. Distance remains immense. Time refuses to behave uniformly. Energy requirements rise toward absurdity. Radiation slowly erodes both machines and bodies. Communication stretches across generations. Entire galaxies drift away through cosmic expansion. And perhaps all of those barriers together are quietly pointing towards something profound. Maybe intelligence was never meant to spread endlessly across the cosmos like ink across paper. Maybe the universe is structured differently, not hostile, not cruel, just vast beyond anything evolution prepared the human mind to comfortably inhabit. There is a certain sadness inside that realization, but also a strange beauty, because limits give meaning to closeness. The stars feel precious partly because they remain distant, A message crossing interstellar darkness matters precisely because it is difficult. A civilization listening patiently through static becomes moving because silence is so immense around it. And perhaps this changes the meaning of exploration itself. Maybe exploration is not fundamentally about possession. Maybe it is about awareness, understanding, witnessing. For most of human existence, people looked upward without understanding what stars truly were. Tiny lights scattered across darkness, permanent, untouchable. Now humanity understands that each star is a sun. Many possess planets. Some may hold oceans, atmospheres, weather systems, perhaps even forms of life staring upward with their own questions. That realization alone already transformed the universe forever, even if human beings never physically walk beneath distant alien skies. We have still learned something astonishing. We are part of a living cosmos large enough to contain endless possibility. And perhaps that understanding matters more than conquest ever could. There is also something deeply human about continuing to dream despite limits. Human beings build telescopes not because galaxies are easy to reach, but because wonder itself feels meaningful. Scientists continue listening for distant signals, not because success is guaranteed, but because curiosity naturally reaches outward. Even now, somewhere on Earth tonight, radio dishes are slowly turning beneath cold skies. Astronomers sit beside glowing monitors studying faint patterns arriving from deep space. Spacecraft continue drifting beyond the planets, carrying tiny fragments of humanity outward into the dark. Voyager 1 still moves farther from Earth every second. A small machine built by fragile biological creatures living on a rocky planet orbiting an ordinary star. Inside it travels music, greetings, images, evidence that for one brief moment in cosmic history, a civilization looked upward and wondered who else might exist. There is something beautiful about that, not because Voyager will likely ever be found, but because the act itself matters. The reaching outward matters. Perhaps intelligence is valuable not because it conquers the universe, but because it becomes capable of appreciating it. A galaxy filled entirely with unconscious matter would still be magnificent. Stars would still burn. Nebulae would still glow softly across darkness. Black holes would still bend space-time silently beneath invisible horizons. But conscious beings allow the universe to witness itself. Through countless eyes scattered across planets and moons, the cosmos slowly becomes aware of its own existence, and maybe that awareness does not require physical unity. Maybe civilizations do not need to merge into vast galactic empires to share something meaningful. Perhaps simply existing together beneath the same universe is enough. The stars may remain physically distant forever, yet light still travels between them. Knowledge still travels, signals still travel. Awareness itself stretches across space-time every time one civilization wonders whether another might be listening. And in that sense, the universe is not entirely disconnected. It is threaded together softly by curiosity, by observation, by questions crossing darkness at the speed of a light. There is comfort in that idea. The cosmos may not be a place built for rapid movement or endless conquest. It may instead reward patience, humility, and careful attention. The night sky becomes less like territory waiting to be claimed, and more like a vast conversation unfolding slowly across unimaginable spans of time. A conversation made not of armies or borders, but of mathematics, light, radio waves, stories, and wonder. And perhaps somewhere far away tonight, another civilization is also reaching the same conclusion. Perhaps beneath alien oceans or unfamiliar constellations, Another species sits quietly beneath dim artificial lights, listening to static, studying distant stars, wondering whether consciousness exists anywhere beyond their own fragile world. Maybe they too have discovered that the universe is too immense for easy travel, too patient for empire, too bound by space-time for simple conquest. And maybe they also understand something else, that even separated by impossible distance, civilizations can still share the same longing to understand the darkness around them, and perhaps that shared longing is the closest thing the universe has to connection. So tonight, as the stars continue drifting silently above our small world, you may find yourself looking at the night sky a little differently, not as a map of future colonies, not as empty silence, but as a vast landscape of distant awareness, countless lights separated by extraordinary darkness, yet all part of the same unfolding cosmos. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. The universe may remain too large for civilizations to ever truly cross completely. But here, in this quiet moment beneath the stars, perhaps understanding is enough. Sleep peacefully, wherever and whenever you may be.